Hi again, here we are. Now, today we are going to speak about adiabatic process. So, any adiabatic process, it's a process in which, okay, the heat transfer is equal to zero. So, when heat transfer is equal to zero, P, pressure, time, the product between pressure time volume to the power gamma is equal to C, is constant. What do we mean by this one? What is gamma? Gamma is what we call adiabatic index, this one, adiabatic index. And gamma, it is the ratio between the specific heat at constant pressure and specific heat and constant volume. Okay? Just like this. So first we are going to derive where this guy comes from, because in some tests, in some exam for GTU, so some people sometimes they ask us for this one. Okay, and this is very important to know. So we are going to just derive this expression here. Okay, so to derive this expression, we will have first to understand what is Q. Okay, Q, heat transfer. From the first law of thermodynamics, we know that Q, it is work done plus what? Plus internal energy, change in internal energy, right? And we will combine this formula, this expression, to another one, that is PV equal to MRT. Okay? PV equal to MRT. Nice? Yeah. This expression that we are going to use here. So here we know, first, I will call this one and I will call this two. First, here we know that for adiabatic process, okay, adiabatic process, heat transfer is equal to zero. So it means that here you get zero equal to work done. Okay, equal to work done. I will just put here what is work done. And we know that work done, it is PdV. PdV. Okay? Whenever there is change in volume, there is work done. Okay, so PdV, change in volume. This dV stands for change in volume. Okay, to have work done, we do not need to have change in pressure. Okay, work done, it is strictly a function of volume of the gas. Okay, PdV plus, what is this guy? We know that this is always mCV delta T. Nice, we know this. This is the first step. Now here, okay, this is the equation 1. Sorry, this one I will not call 1, I will call the equation I. Okay, I comes from 1. And from here, what will I do? I will just do, and we know that this delta T can be also, as I said, internal energy, it is a function of time. So this delta T can be also changed by dt. Okay, dt, delta T, this is the same with dt. As we did like this one, the work done is a function of volume. So delta V, it was changed by dV. It's the same I can do with this one, and I will do this later on. Okay, I just forgot to write in here, but it's okay, you can stay like this, and in the end I will change. And see now, here we have PV MRT and PV MRT. Okay, so we know that this pressure, volume, and temperature, they are all variable. They can all change. Okay, so here we will apply the rule for the partial derivative. Okay, considering the P, V, and T as a variable, okay, not a constant, because they change here. As we have seen with the whole processes, there was a process, the temperature change, volume change, pressure change, and so on. So we will apply partial derivative for this one. Okay, here applying, if we apply to this second expression, applying partial derivative concept. Yeah, partial derivative concept. Or we can say differentiate. If we differentiate this expression or this one, differentiate this one, you will get this guy. So whenever we have two differentiable expression, okay, and like suppose we have, I will use too many math because math is in here all the time. We have two function, f of x and gx. They are deriving. If I derive this one, it will be first f of x derive, gx do not derive. Okay? Then plus f of x will not derive, then gx will derive. This is the same that I will apply to this one. So this one will be first, if I derive d pv, okay, and I will derive also d mrt. Okay, what will I get? This mr are constant, so they will be out. Mr. This will be dt. And I derive this guy. This guy is a product. This is a differentiated value, and this one is also differentiable. So we can just apply differentiative. We apply this rule one. Okay? So what will I get? We'll get d, p, and v is constant, plus, okay, plus v is not constant, and here, sorry, p is a constant here. Now p will be constant, and v is the variable here. Okay, that's the one. We just apply product. Okay, product rule when we have two functions multiplied for partial derivatives. Okay, this function is a function and this is one. We just differentiated these two functions. Okay, so okay, we apply just this derivative on this one. So d dp is equal plus p dv is equal to mrt. Okay, nice. What we are going to do here, see, here you have dt, and here delta t is also dt. I will just pick up this dt and I will substitute in there. Okay, this dt. Now dt is what? Dt is this guy. Okay, will be v dp plus p dv upon mr. Okay, upon mr. Okay, on mr. On mr. Okay, I will substitute this I2. Okay, I will substitute this I2, this 2i in only I. Where is I? I is this expression. I will substitute this one in this one. Okay, delta T, it is the same. Change in temperature, it is the same of differentiated temperature. Okay, dt. I will substitute now. So what will I get? Okay, I2, it is dt. Let me just remember you. P dv plus v dp upon mr. Okay, and I, it is 0 equal to p dv plus mcv, then dt. Delta t, it is dt. I will substitute this guy in this, dt in dt. So what will I get? Okay, what will I get? Or I can just directly equalize this dt and this dt. I can just directly equalize them. Okay, it's up on you. Okay, it is up on you. It's up on you. Yes, as I was saying, we just have to find what is this one in here. You just substitute this one and this one. So you'll get 0 equal to p dv plus mcv dt. Okay, dt. Okay, sorry, in the place of dt, I will write down all the expression there. Let's minimize this one. Okay, will be 0 equal to p dv plus mcv. Then here I will write down this expression, p dv plus v dp upon mr. Okay, m will cancel with m. Okay, and here this cv upon r, this will be cv upon r. So 0 will be p dv plus, okay, cv upon r. This can be like this one. You get cv upon r. Then here we will get p dv plus VDP. Okay, so as this is true, okay, this is true, as we can see, this is true. So what can we do here first, okay, to find out our how can I say, to find out the relation between, because this looks like it is very complicated to find out what is someone, how to find this and how to find that. So see here, so what you'll do is what you will just substitute, or how can I say, you just multiply all this expression. Okay, you can multiply all this expression by directly the okay. Now from here, as we were saying, so CV upon R. So now I will just multiply all the terms here by R. Okay, just multiply all the terms by R. You'll get 0, and here it will be P dV times R, and here you'll get CV P dV plus VDP. Okay, now I know that R is CP minus CV. Nice. So I'll get 0 is equal to P dV CP minus CV. Okay, here it is plus, sorry. Okay, CP minus CV. Then I'll get plus CV P dV. Okay, CV P dV plus CV VDP equal to it's equal to 0, the same thing. 0 is here. Okay, so PDV CP minus CV plus CV PDV plus CV VDP. From here, okay, you have just to do the same. Just extend this guy also. It will be P dV times CP minus P dV, and here CV plus CV P dV plus CV VDP. Okay, now see this guy P dV CV is the same of P dV CV. These are equal, so they can be cancelled out. Okay, just like this one. Okay, just like this. And here, what you get? You get this one. 0 is equal to P dV. Okay, CP plus CV VDP. Is that okay? So it implies that here I will get, okay, I will get dV. Just divide all the expression here, if you feel like, by CV, or you can just do this one, CP, okay, CP P dV is equal to minus CV, send this guy to here, minus CV, then V dP. Okay, this one. So this expression that we have here, I will just use in another page. It is the same. So it is CP P dV is equal to minus CV G dP. Okay, now see, here I will just pick up volume, here come here, pressure go there. Okay, volume come here, pressure go there, and this CV also can go there. So we can just come and divide it all by CV. Okay, and V. Divide CV and V, because this dP and this pressure must go there outside. Okay, just CV, and you can also divide by P. Everything here divide. So here we got CP, P, dV divided by CV, V, and P minus CV, V, dP divided by CV, V, and P. So just cancel out this one and this one, and also this one, this one, this one, and this one. So CP dV upon CV time V, and here it will be minus dP upon P. Now see, CP upon CV, we said that the index, adiabatic index, it is what? CP upon CV. Okay, this is adiabatic index. Okay, so I can just substitute this one by lambda, gamma. Gamma dV upon V is equal to minus dP upon P. Now I just apply integration in both sides. Okay, just integrate both sides. It will be lambda out, it will be dV upon V equal to minus integration of dP upon P. Okay, so just integrate this function. It will be what? It will be here lambda, here L, V upon V, V upon V. So it will be what? This one will be minus ln of what? Sorry, it is dP. Okay, dP. It will be ln of P. Okay, and here it will be what? Gamma ln of V. Are we together? Then what we have to do in here? What do we have to do? So see, ln in here, ln in here. This guy come here up. Okay, and this guy can come here. This minus can come here also. Yeah, if you feel like it's up on you. But see, this guy will come here. So this one will go here. Okay, this will be V. This is all math. Okay, V, and this guy come here plus what? Plus ln of P is equal to 0. Okay, then this and this. Okay, because after you integrating this one, you can just add this C. Okay, so that this one, sorry, this one, not here. Integrate after integrating, no integration, this one plus C. Okay, just because there is no limit, so we can add plus C. This C is a constant number, so that here I cannot stay 0. Okay, just please C. I'll take this one, it will remain C. So here this one will be what? Will be ln, okay, of P V to raised to gamma time P is equal to C. Okay, now from here just directly go, you can just go and say this one will be V raised to lambda or raised to gamma time P will be equal to, here it is log in the base E. So this E, definition of Euler, definition of logarithm, this E will go up. So this will be Euler to the time C. Okay, so this Euler to the time C, it is also constant. So yeah, in this way you can just say V raised to gamma P V raised to gamma is also a constant. So that is the way we use to prove that this guy, it is true. So that this is the expression for adiabatic. Okay, for adiabatic process. For adiabatic process, this is the governing equation. So this one. Okay, and even from here, okay, even if I did not calculate it this way, okay, even if from here, if it were from here just only, okay, see, you can also come this one. This will be what? This should be ln V raised to gamma equal to ln of P. Okay, it should be like this one. Yeah, should be like this one. And then here I will just go back. Yeah, do not go this way, just okay. Yeah, just this one. Lambda, gamma, ln, and then call it back. It will be ln of v raised to gamma plus ln of p. And here you have this one. This is the one. This one is this one equal to c. So v raised to gamma times p equal to Euler to the power c. This Euler to the power c is a constant also. So p v raised to gamma is equal to c. It's a constant. So yeah, in this way you can just prove that this is the equation for what is the name? Adiabatic process. Okay. So then it is proved the equation for adiabatic process. This is this one, as you can see here. Thank you. Now in the next video we will start finding what is the work done, what is the PV relation between them, and so on and on. Thank you very much.